Okay, good morning, ladies and gentlemen. So I'm going to talk about predictive maintenance, automated fault detection, which I think is the future. And I'm coming from Klimacheck. We have a long experience of performance analytics. I started in the mid-80s when there were heat pump boom in Sweden to try to figure out the performance of systems in the field. And Klimacheck was started 2004, and now we have more than 1,000 systems on our online platform and supplied almost 1,000 of portable performance inspection tools. And of course, a lot of things are happening now. We started online monitoring 2007, and now predictive maintenance is on everybody's focus. And I think it's going to change the industry totally. Traditionally, there is a black box of the refrigeration process. Nobody's looking inside except for when somebody once or twice a year come out and check that it doesn't trip. But there is no focus on performance. Nobody is responsible for how the system operates in most cases. So there's a huge saving potential by focusing on this and detecting deviations long before they create a failure or downtime. So what we do is that we apply thermodynamics. We measure the refrigeration process, which makes it possible to, in 20 minutes, hook up the sensors and have COP, condenser efficiency, compressor efficiency, everything at the same level as a test rig in a manufacturer's site. So we have supplied about 50 manufacturers with development test rigs analytics. So I promise you it works. And for those that think that we need a flow meter, there is a flow meter in every refrigeration process. If you look at the compressor and believe in the energy laws, if I put energy into the compressor, it will have to come out. Otherwise, it will melt. It comes out in two ways. One is enthalpy increase of the refrigerant, and then a small part is a heat loss from the shell. And that heat loss is small, and it doesn't change a lot unless you have active cooling of the compressor. If you have active cooling, we need to model that active cooling. But that is a few percent of the market. It's interesting because it's large industrial plants and so on. But most systems, you can make a very simple assumption on heat losses and get within a few percent of the COP, which is better accuracy than if you use flow-based measurements on the water side. And on the air side, it's almost impossible in the field to measure flows and humidities in a dynamic system. So when we apply the thermodynamics, I showed you this basic process, but of course you can do it for multi-stage systems, economizers, and CO2 booster systems. The thermodynamics is valid for everything we do. Then we have a perfect service protocol. And this is you can monitor it 24/7 and test, indicate any deviation long before you have a failure. Most compressor failures in the industry is not because of that there is something problem in the compressor. It's because you're running it in a poor way. So there is almost an explanation in the history of how you operate before it fails. And you can detect the faults on component level this way. This is just bragging a little bit that the National Renewable Energy Laboratory in US, they made an evaluation of the automated fault detection systems on the market. So you see that there are some famous names like Carrier Train, York, and so on. And they didn't have automated fault detection that can pinpoint the problem to the component. But Klimacheck has that. One interesting application is, of course, if you build the energy signature for the plant, most plants would reflect both the performance and the load is dependent on the outdoor temperature. So you get an energy signature that's very characteristic for that site. And if you track that, you optimize your system, you get a nice profile, which we call the energy signature. And if your system is deviating, then it's changing something in the system. So either it's a performance change on a component level, which we have in the performance analytics, we have every component, but it could, for example, be a refrigerant leak, and that will have an impact. So you can detect, depending on system, this might be a very good way of detecting leaks if you have a receiver. Whereas if you don't have a receiver, normally there would be other parameters that would be indicating much sooner than the... And we did a project for the German energy agencies. We built a benchmarking platform for them because they identified that it's not going to be... people with refrigeration site, they think it's okay if it's cool. If it cools down to the temperature, they think it's okay. So how do you drive energy efficiency when everybody is satisfied with that it reaches the temperature? And so this has been a big challenge. So they said that we need to develop benchmarking so we can say that what is good and what is bad. So then we were awarded the contract to build that benchmarking platform. So it has all the performance contracting that we have. It has the energy signatures. But then also, if you then benchmark this per square meter, okay. So then the energy signature takes care of if you are in this country, this temperature. So because you only compare at a certain outdoor temperature. So if you compare a site here at 10 degrees and in Stockholm at 10 degrees, you can compare them. But of course, they might be different size. So if you then benchmark on square meters, you are being able to benchmark regardless of size. Of course, you cannot compare a supermarket with a hotel. So you also need to categorize your systems to what type of, if it is a supermarket or a shopping mall or office building or hotel or something like that. But when you start making these categories, then you can benchmark. And of course, a customer can benchmark their systems. And you can benchmark on square meters. Of course, you can benchmark in a supermarket. Maybe some have a lot of refrigeration, some have less. So then typically there are some supermarket chains that are working with meter display case. So they can normalize low temp to medium temp and cold rooms to medium temp. So they say that this has so much cooling. So you can develop whichever normalization you want. But this project is... it's basically finished now, and so we are now running it, and then they are going to decide on how they're going to push implementation. But I think it's very important with benchmarking for the future. Then with the basis of energy signatures and performance analytics, we have started to implement machine learning, and that is really going to be a game changer, because of if you look at compressor efficiency, for example, that is changing. So if I have a slide regulated screw, maybe the compressor efficiency is 30% at part load, and it's 72% at peak performance. So to set up the alerts for that, you would have to take into consideration different load conditions to be able to detect with a good accuracy. But if you have a digital twin of a slide regulated screw compressor, then you only need to say that I allow X% deviation. So it saves a lot of time and it increases the accuracy drastically. So with that thought, I started to work with two different institutes, the Royal Institute of Technology in Stockholm, to apply AI, machine learning technologies on that. And this is going to be such a powerful tool. I mean, we have only worked with it for 1 year, but we have a physical model behind, which make machine learning extremely powerful, because we know exactly what is triggering the changes. So there's all physical laws behind it. They are fairly complex because there are many parameters affecting it, but we know what they are. And the digital twins, they are generated based on training of a lot of data. So this is just showing condenser efficiency, where we have trained it on one system and we are applying it on another. We don't need to have data for each system and train on to be able to set it up. Because, I mean, the condenser is the same on many others. We don't even need to have exactly the same condenser, because of this happens to be a plate heat exchanger, but so we cannot use a plate heat exchanger model for a tube and shell or an air condenser. So we need to, again, use a similar type, but a plate heat exchanger condenser will behave fairly similarly if it's a 10 kilowatt, 100 kilowatt, or megawatt system. The physical procedure is the same, so it works even much better than I hoped. So here you see at different capacity, you see how the condenser efficiency is changing between 75 and 95. So the more load I put on the condenser, of course, the efficiency goes down. So when it's 95, I'm using part load, and the condenser is really oversized for that. So it's really highly efficient at that. Okay, so then we see that the digital twin makes my life much easier. I can just trigger a deviation parameter rather than having to try to arrange warnings for that. And this is two different heat exchangers, two different units. And you can see that the deviation is about 1%, 1.5%. So, and this is including all sensor deviations and so on. So it becomes extremely powerful tool. So just showing this in enlarged. Here it's looking at charge. So in a system where you have we don't have a receiver, the buffering is either in the evaporator and the condenser, depending on what type of system you have. But if you have a system with a traditional expansion device, your buffering is in the condenser. So the subcool is reflecting the refrigerant charge. And as it varies in this case between what is 7 and 10, of course, to have a fixed level, I would have to, if I want one level, I would have to set it on 6, which if I then measure on the condition where it should be 10, I have a lot of difference before I get an alert. But in the case of using a digital twin, I can accept much slower tolerances and follow it much closer. So it will make it very much easier for us to trigger very precise early warning. This is showing, some of you might have come across that there is problems with some compressors when you have tandem connection. So if one of them leaks backwards, the other one will fail. Because there's a refrigerant going through the standstill compressor over to the operating compressor, which brings too much oil into that compressor, and then it pours out the oil, and the oil comes back saturated with liquid refrigerants. That cools down the compressor, so it looks like it's super efficient. Of course, that is a fault. When you cool the compressor, it will damage the lubrication properties of the oil. So that creates failure, maybe 1, 2 months, 3 months later. But there is a huge amount of compressors failing in Europe every day because of this particular. You would get similar if you have where you're running part load, the expansion device, if it's not properly adjusted for operating a part load, you get the same problem for the compressor, that the expansion valve becomes unstable, it throws liquid into the compressor, and you see it immediately on that you get a fictive increase of compressor efficiency. So you can catch it when it starts occurring, fix the problem, and avoid compressor failures. this is showing where we train on the SEI. SEI is System Efficiency Index. So instead of talking about COP, which is changing with each operating condition, we like to talk about System Efficiency Index, which compares the COP with a Carnot cycle at the ambient conditions you're working with. So if you have a chiller, you look at the average cooling water, average chilled water. If you have an indefinite heat exchanger, indefinite flow, that would be the temperature level this system is working with. Then you can split your efficiencies on condenser, compressor, evaporator, and cycle. And if we look at total system efficiency, this is two different chillers sold on the same specification, but this is how they actually operate. So this is, you get a little bit surprised over, I mean, this is a 50% difference in energy consumption on two new sites sold on the same specification. Like, what? So this needs to receive much more focus. This is an example from a shopping mall in southern part of Sweden. They were running, and you see the blue is the energy signature from before, and then they were here. They recommissioned the controls totally, and then they reduced the energy consumption. Oops, sorry. They saved 141,000 kilowatt hours during one summer for air conditioning. And here they had a lot of tripping of the compressors on oil leaving the compressor. And when you look at this, this is a before and this is after. And this is extremely common, that the chiller has its own control and this building has its own control. You need to make sure that these works well at different load conditions. And nobody has responsibility for that. Equipment owners, they hear it's, oh, it trips, but that's because of the consultant or it's because of the plumber or... So there's always this debate on whose fault is it. And you just need to make sure that they work together. And it's possible. This is another, where you apply performance analytics and strategies. Peak shaving. This is an IKEA store in Sweden. Looking at peak shaving. They could reduce the peak load between 8 and 11 in the morning with 50%, or to 50%. And they actually saved 20% of the energy because they were running more at night when it was colder outside. So it was extremely good proof of that you need to look at your system. You need to be strategic in how you run them. It's not just allowing them to run. This is another case from US. They have implemented Climacheck's performance analytics on 25 hospitals, I think, now. So it is 78 chillers. So they recommissioned this, and then they were monitoring during 2 years. And during these 2 years, on these 78 chillers, there was 109 identified things that needed to be corrected. So, and the thing with our technology is that there is a lot of things affecting it. They're affected by the cold side, warm side, internal, and you need to get it right. And sadly enough, most sites have not been correctly done. But even when you have done it, things happen. And it's not one thing, it's many different things. And you need to be able to pinpoint it effectively. So there's a lot of documentations, both in this one, there's a description of definitions for System Efficiency Index and so on. Annex 52, this is actually for ground source heat pumps, chillers. But everything in this, I would say, will be generally applicable for any refrigeration, air conditioning, heat pump process. So very good advice on how you monitor long term. We try to apply everything there. And predictive maintenance, we try to push that this is the future. CoolSave is a report on industrial refrigeration improvement possibilities. So my time is out, but if you have some quick questions here, or I forgot to put the hall 9336. We will be there. If somebody wants a business card after here, you can just stop me and we'll get one. Thank you very much. You have 1 minute for question. Any questions? Nobody dares. Please see us at the hall 9336.